Okay, so when you use law of sines to find missing sides, there's no problem, you get unique answers. But there is a little bit of difficulty when we use law of sines to find missing angles because sine is not a one-to-one function. So I say here it can be ambiguous, meaning there could be more than one triangle that solves this thing, and we just have to look at it and see and give all possible solutions. So example 3, solve triangle ABC where angle A is 30 degrees. The opposite side of that, side A is 8, and side B is 7. Okay? So we can set up our law of sines ratios here. And if we use what we know about A and B here, we have sine A over A equals sine B over B gives us this expression. And we can multiply both sides by 7 to get sine B by itself. And then we could use, well, first of all, let me say we have sine of angle B equals 0.4375. The problem is between 0 and 180 degrees, the top half of the unit circle, there's two angles that have the sine value of 0.4375. Here's a picture that I made of that. And there's the angle in quadrant 1, which is what inverse sine is going to give me. But then there's the bigger angle that puts me in quadrant 2 that has the same y value, so it has the same sine value. And both of those could potentially fit in a triangle because they're less than 180 degrees, so we have to check them out. The second one may be too big depending on the other angles. So I'm going to start by labeling a case 1 and a case 2, and there may be no case 2 depending on the size of the angles. But case 1, we can just take the inverse sine and we'll get the angle back in quadrant 1, and I've rounded it here. But so the inverse sine of 0.4375 is 26 degrees. So that's the angle in quadrant 1. Okay, but there's also this bigger angle in quadrant 2, which is just 180 degrees minus 26. So whatever we get from our calculator with the inverse sine, we have to subtract it from 180 and also consider that angle, because 26 degrees and 54 degrees have the same sine value. They both satisfy the sine of B when we round as 0.4375. So we have two possible cases to consider. But if you look at this, 154 degrees plus the 30 degrees we already have is 184. That's too big. It's bigger than 180. So in this problem, we only have one case. The second possible angle is actually too big. It won't fit. So we just finished case 1 and we've solved the problem. Okay. So to finish that, we now know that angle B is going to be 26 degrees. We already knew angle A, so we just subtract from 180 both of those. We get angle C's 124 degrees. And then we can use law of sines again. We have sine A over A equals sine C over C with the 124 degrees. And I've solved several of those now in the videos, so just cross multiply and work it out. And you'll get that C is 13.3. Okay, here's another example, same type of problem. So this time we start off with sine A over A equals sine B over B and solve, multiply both sides by 7 to solve for sine B. We wind up with sine of B is about 0.75, 0.7499. So again, there's two possibilities. Case 1 could be that we get the inverse sine of that number, which is 49 degrees in quadrant 1. Potential case 2, if we subtract 180 to get the one in quadrant 2, we have 131 degrees. This time that fits. 40 degrees plus 131 is only 171. There's not a lot of room left, but there is room for another angle. So we have to finish case 1 and case 2. So if we continue, if we ignore case 1 for a minute and solve all of case 1, if we ignore case 2 and solve all of case 1, we have the 49 degrees for angle B. We were given the 40 degrees for angle A. We can just subtract from the 180 degrees in a triangle and get that angle C is 91 degrees. So we have close to a right triangle, but not quite. I can find side C using the law of sines. So we set up sine A over A equals sine C over C and solve that, and we'll get that C is 9.3. So that gives us all the information for case 1. Then we have to repeat that for case 2, where we assume that B was actually the 131 degrees, and we can find that angle C is then only 9 degrees. And we use law of sines to find the missing side in that case of 1.5. Okay? So sometimes, and you don't know until you get in and you check it, but sometimes law of sines can have two answers to a triangle. When you have to find a missing angle, it could be the value in quadrant 1. That one, as long as you get a value that any triangle exists, the one in quadrant 1 is going to work for you. But we have this other angle that's between 90 and 180 that could potentially work in a triangle. It did on example 4, it didn't on example 3. You just have to look at the angles that are there and test it and see if it's more than 180 degrees. Okay. Then I have one last example. It's kind of like quadratics. There could be 2, 1, or actually no solutions. Here's one where you can't possibly have a triangle. Again, I don't know that in advance other than I've already worked the problem before, but we're going to see when we do it that it comes out to be no solution. So solve triangle ABC where A is 48 degrees, side A is 50, and side B is 160. I set it up like the previous two problems, and I get sine of 48 degrees over 50 equals sine of angle B over 160. And I try to solve this thing. I multiply both sides by 160, but here's the problem. I get that sine B is 2 point something. Sine values are the y coordinates on the unit circle. They have to be between -1 and 1. There is no angle that's going to give me 2.3 something for its sine value. So no such triangle exists. There's no solution to this problem. I cannot find a triangle that has these specific measurements.